Hello students, welcome to Vyas Edification Kota. In this series of NCERT discussion, we'll continue further with Mathematics class 12th, and the chapter that we're dealing with is integrals. It is time to discuss exercise number 7.3. Now this particular exercise is based on applications of substitution basically, and these applications actually involve something called trigonometric identities, right? So from the chapter trigonometric functions, you have studied something called sin x plus sin y is equal to 2 sin x plus y by 2, cos x minus y by 2, something of that sort, product to sum to product, right, something of that sort. And accordingly you have also studied something called multiple and submultiple angle formulae. So all of those things are useful for integrating various types of functions, as we'll be discussing over here. So along with the questions from the point of integration are pretty simple. They are not very complicated from the point of view of integration, but they have to be simplified in a form which is integrable, right? That's very important. So that simplification process requires some formulae of trigonometry, right? So along with the questions, we'll be seeing the required formulae and you'll be revising everything with us. We'll be going through all the concepts and understanding everything with us, right? So let's begin with the first question over here. The question says, okay, find the integrals of the functions in exercises 1 to 22. That's the question. And you're given sine square of 2x plus 5. Now that 2x plus 5 is actually not such a big problem. There's another big problem over there, and what is that? Sine square. Okay, we know the integral of sine, but we don't know the integral of sine square, right? So how do we find the integral of sine square? Let's take a look at this. Integral of sine square x dx. This is question mark. So this sine square x cannot be solved directly, but we know one identity of this sine square which says, okay, cos 2x is equal to 1 minus 2 sine square x. Oh, this is an identity of cos 2x, yes. But the important thing is that power 2 was an issue, so power 2 has to be reduced to power 1 in some manner, right? So reducing the power to power 1 will actually convert this x into 2x in a multiple angle, right, in this manner, and that is what we'll be doing. So from here I observe that sine square x, this sine square x is actually equal to 1 minus cos 2x upon 2. This is what we have, and this is something which you should remember. This is something that you should remember at all times, right? Okay, so sine square x is equal to 1 minus cos 2x by 2. Therefore, integral of this I equals integral of sine square 2x plus 5 dx can be written equal to, there's a 2 in the denominator, 1 minus cos of twice the angle. So let's bring that 2 outside, that is 2 in the reciprocal, 1 minus cos of twice this angle, which is 4x plus 10. This is what you get, and this is what I want to integrate. Now integration of 1 is not a difficult thing, yes. This is 1 by 2 is outside. Integration of 1 is simply x, right? Cos of something, if that function is a linear function, we can integrate that very easily, right? This 4x plus 10 can be substituted as t, and you can replace 4 times dx with dt. Or in other words, you can directly take this as a linear function of x and integrate without worrying about anything. In the end, you just divide by 4. Divide this particular term by 4, not the whole term. So you have cos of x. What is the integral of cos of x? That's sin x, right? So you get minus of sine 4x 10, and this sine 4x plus 10, there is a coefficient of x which is there. You have to divide with that 4 over here. A constant term will be added. That's a complete integral, yes. Let's simplify this further. This is actually x by 2 minus 1 by 8 sine of 4x plus 10 plus constant, and that is the required answer for this question, as you can see, with the help of this and another result which we have been seeing since the previous exercise and since the first exercise only, that if integral of fx dx is equal to gx plus c, then integral of f of linear function, linear polynomial of x, this f of ax plus b will be equal to g of ax plus b whole divided by this a plus constant, right? That's what you have. If this is true, then this becomes true, right? And this can be proved with a simple idea of substitution we have seen in the previous exercise, right? Okay, so once again, the integral of cos something is sine that something and divided by that 4. That's the important thing, and that's the final answer for this first question, and that's a complete solution for this question over here. The second question says that we have to integrate sine 3x into cos 4x. Okay, but they are in product, right? Okay, so that is an issue. Yes, that is an issue, because had they been in sum or difference, we could have integrated them directly, right? Oh, but they're in product, right? So we'll have to convert them into sum or difference, because we don't know the integral of sin x into cos x, right? We don't know that. So let's try to convert sin 3x into cos 4x as this is product of two trigonometric ratios. We'll try to convert it into sum or difference of two trigonometric ratios. And the result that I recall is, these are two different angles. 2 sin A cos B will be equal to what? I'll use this result, right? And this result is directly brought from trigonometry. 2 sin A cos B is sine of A plus B plus sine of A minus B. This is what we have. Okay, this 2 can be taken over here in the denominator. This is what you'll have. So sin A cos B will be half of sin A plus B plus sine of A minus B. So using this result, I is, which is equal to integral of sin 3x cos 4x dx. If this is the one, then this simplifies further to, there will be a half, okay, and along with that there will be sine of A plus B, okay, sine of A plus B, which is 7x, plus sine of A minus B, okay, 3x minus 4x, which is minus x, okay, dx. This is what you get. Right? So up till now we are not integrating actually, we are only simplifying this integral. This half can come out, this integral of sine 7x minus sine x, which I have, dx. Now I'll integrate this, but first observe, sine of minus x will be minus sine x, right? I've written that. And once we reach this stage, now I can integrate, which tells me that I will be further equal to, half is okay, the integral of sine 7x, what is that? That is minus of cos 7x. So you have minus cos 7x. Oh, but instead of x you have a linear function of x. Yes, we have 7x. So you'll have to divide by 7 over here. Yes, that's important. Okay, and you have minus of, you have sin x, the integral of sin x will be minus of cos x. Okay, this becomes plus cos x. And do we need to divide by something over here? No, we don't need to divide by anything. Okay, plus a constant. That's what you have, right? So what does this convert into? This is minus 1 by 14 cos 7x plus 1 by 2 cos x plus constant, and yes, that's the required answer for this particular question, as you can see over here. In the third question, we have cos 2x, cos 4x, cos 6x. Oh, we have more products over here. Right? We have product of 3 terms. And for solving this, we need one identity which relates cos A, cos B, converts cos A, cos B into the sum or difference. Okay. So for that, I recall that cos A, cos B multiplied by 2 is equal to cos of A plus B plus cos of A minus B. This is what I recall. Right? Using this identity, I can simplify that expression. Using this particular identity, I can simplify that expression, right? And which two cosines should I take? So instead of taking 4x, let's take the two extremes, cos 2x and cos 2x, cos 2x and cos 6x, and see where does that take us. So we have I equals integral of cos 2x cos 6x together into cos 4x dx. Okay. Once you have this, cos 4x will remain as it is, and you can write the remaining as half of cos cos 2x into cos 6x will convert to cos of a plus b, which is cos of 6x plus 2x is 8x plus cos of a minus b. Now 6x and 2x can be subtracted. This is 4x. Oh, you could have written minus 4x as well. Yes, I could have written minus 4x as well because 2x is written before. So you can take a as 2x, b as 6x. But do you remember that cos of minus x is also equal to cos of x, right? So it will not make much of a difference because this product can be written, cos 6x can be written before and cos 2x can be written later. We can take a or b interchangeably as well, yes. And so we need not worry, and this is what we get. Okay, with respect to x, this is integral with respect to x. What next? This half can be brought outside this integral, okay. But still you have a cos 4x into cos 8x plus you have cos 4x into cos 4x, okay. So you have cos 4x into cos 8x plus cos square 4x dx. What do we do in this particular case? Okay, if you observe carefully, cos 4x into cos 8x can again be converted using that result as sum of two cosines, yes. Moreover, this cos square 4x, now in one of the previous questions we saw sin square x can be converted. This power can be reduced by converting into multiple angle, right? And that is what you'll be doing. So 2 cos square x is also equal to 1 plus cos 2x. This is another result, right? So you remember this result with the help of cos 2x can be written as 2 cos square x minus 1. Therefore, 2 cos square x can be written as 1 plus cos 2x, or cos square x can be written as 1 plus cos 2x by 2. And that is something you should be using. Okay, so we can simplify this further. Yes, half is okay, integral is okay. In this bracket, let's convert this into a curly bracket. Cos 4x into cos 8x will convert into half of cos sum of the two, which is 12x. Sum of the two, which is 12x. And the next thing that you need to do is take the difference. Okay. And we'll take the difference. How will we take the difference? Plus cos of a minus b. Oh, 4x minus 8x or 8x minus 4x doesn't make a difference, as we have seen. This will be cos 4x. Okay. This is this particular term simplified. Plus you have this term, cos square 4x. That can again be written with the help of that as half times, in the bracket you have 1 plus cos of double this angle, which is 8x. This is what you have, right? So this curly bracket opens the first term, and the second term this curly bracket gets closed. Okay, respect the brackets, right? Don't miss out on the brackets, and if you do that, you will not face much difficulty. So this half and half can be taken out common from these two terms, and we'll have a 1 by 4 outside. Inside the integral we have cos 12x plus cos 4x plus 1 plus cos 8x. Okay, that's a complete expression in the bracket, and this is what we want to integrate now. This is in a form which is integrable. That was the first thing that we wanted, and we have reached this stage where we can integrate, right? Therefore, I is further equal to 1 by 4 is outside, and I can integrate this cos 12x. Now cos 12x will be equal to what? Cos 12x will be simply sin 12x. The integral will be simply sin 12x, but we'll have to divide by that 12, right? So this is sin 12x upon 12. Okay, next let me take this cos 8x, right? These are all in addition. We can take this term next. This will become sin 8x upon 8. The next term will be cos 4x, which will convert to sin 4x upon 4, and this 1 will convert to x. Oh, that's a complete expression. Yes, 1 by 4 is outside, and you'll add a constant term over here. That is my final answer. Yes, at max you can multiply this 1 by 4 inside this bracket, and you will get 48 over here, 32 over here, 16 over here, and x by 4 over here. That is what you can do. You can leave the answer at this stage, or you can write it as sin 12x upon 48 plus sin 8x upon 32 plus sin 4x upon 16 plus x by 4 plus c. That's the required answer for this third question, as you can see over here. The fourth question says that we have sine cube of 2x plus 1. And how do we handle this one? So sine cube of anything can be handled in two ways. What are the two ways? Let's take a look at this particular question using one of the ways first. So I is equal to sine cube 2x plus 1. Now this is a linear function, linear polynomial of x. This will not create a problem. This sine cube is creating a problem for us for integration, right? And we can use an idea of substitution. What's that idea of substitution? That we can replace this sine cube, you can break the sine cube as sine square and sine. And you can write the sine square term as 1 minus cos square 2x plus 1. This is what you can write it as. Okay. This is sine square 2x plus 1 and there will be another sine of 2x plus 1 waiting outside. Okay. And now I can use substitution. What kind of substitution do we want to use? Okay, this is a complicated expression, but I can substitute cos of 2x plus 1 equals t. Once I do that, the derivative is waiting outside. Therefore, substitution will be useful. So what is the substitution? Let cos of 2x plus 1 is equal to t, new variable t. So the derivative of cos is minus of sine 2x plus 1. Then you need to differentiate this 2x plus 1 since we are applying the chain rule. This is 2 times derivative of x is equal to dt. Okay, I reach this stage and I realize, okay, this times this dx is present over here. And 2 and minus will go over here in the denominator. So I'll have minus 2 in the denominator. I can make this substitution and this integral will convert to 1 minus this cos of 2x plus 1 is nothing but t square. Okay, and this whole expression is dt upon 2 with a minus. So this is minus 1 by 2 in the product times dt. This minus 1 by 2 is not creating any problems. It will go outside the integral and we can easily integrate 1 with respect to t and t square with respect to t. So this will be minus 1 by 2 at the outside and integral of 1 will be t. Integral of t square will be t cube upon 3 plus a constant term. This is constant of integration, right? So we have this expression. Okay, let's multiply them together. This becomes minus 1 by 2 times t. And what is t? T is this expression, cos of 2x plus 1. Okay, then you have minus 1 by 2 and minus 1 by 3. That becomes plus 1 by 6. And you have t cube. T cube will be cube of this, cos cube 2x plus 1, and you have a constant of integration. This is the final answer for this question. This is the final answer for this question. But it is using this idea of substitution. We can follow another approach for integrating sine cube of something, right? Sine cube of that linear polynomial. So sine cube can be converted with the help of this particular result. Sine 3x is equal to what? This is 3 sine x minus 4 sine cube x, right? This is one result that we remember from trigonometry, that sine 3x can be expanded as this, and therefore sine cube x can be written as 3 sine x minus sine 3x. What I have done is I have brought this over here, sine 3x goes over there. There was a 4, I will divide with this 4. Okay, and this is the formula for sine cube x. What you have done is actually you have reduced the power and you get multiple angle, that is sine 3x over here. Integration of sine x and sine 3x are simple. Yes. So alternative approach of solving this integral could be I equals integral of sine cube 2x plus 1 dx. Okay. This tells me that I will further convert to integral of, there will be a 1 by 4 outside. Okay. And in the bracket you will have 3 times sine x, which is 2x plus 1 over here, minus sine of 3x, which is 3 times this angle. What is that? 3 times 2 is 6, x plus 3. This is what I get. Curly brackets closed. Yes, these are the two terms with respect to x we want to integrate this. Now how do we do that? 1 by 4 is not creating any issue, 1 by 4 will come out. Integral of 3 times sine this, once again 3 is not creating a problem. Sine of something, integral will be equal to sine of x, the integral is minus cos x. So this will be minus of cos 2x plus 1, but you only need to take care of one thing. What is that? That we have to divide by this 2. Yes, divide by this coefficient of x over here. What else? This is minus of sine, so the integral will be equal to minus of cos. Minus will become this plus 6x plus 3, and you have to divide by the 6, bracket closed, plus a constant of integration. That's the final integral. So this will simplify to minus 3 upon 8 cos of 2x plus 1. And what do you have? 1 by 4 and 6. This becomes 1 by 24 cos of, this is actually 3 times 2x plus 1. You can write it as 6x plus 3 only, but this is actually thrice of this angle plus a constant of integration. So this is another form of that same answer. What do you mean by another form? These are looking very different. Yes, these look very different, but if you observe, you can expand this by using the identity of cos 3 theta, and what you will get is that very same thing will come out. Right? That exact same thing will come out once you use this particular result of cos 3 theta. So you can interconvert between these two forms with the help of trigonometric identities again, or you can find the answer in this way, you can find the answer in this particular way. Now, this interconversion, I can leave it to you, I suppose. Yes, the identity that you will require is that cos 6x plus 3 is actually cos 3 theta. Cos 3 theta is 4 cos cube theta minus 3 cos theta. This is the identity that you will need. And just to give you a glimpse of the steps, let's write this. This cos 3 theta will be 4 cos cube. Let me write the term. 4 upon 24 will be 1 upon 6 cos cube 2x plus 1. So that's 1 upon 6 cos cube 2x plus 1. It's matched, right? The other term that you'll get is minus 3 upon 24. Okay, and that's minus 1 upon 8 actually times cos of 2x plus 1. Minus 1 upon 8 cos 2x plus 1 minus 3 by 8. So minus 3 by 8 minus 1 by 8 will add up to minus 4 by 8, which is minus 1 by 2 cos of 2x plus 1. They are exactly same. With the help of this simple thing, you can observe that. Yes. So both the methods are correct. Yes, both the methods are correct. Both the answers are also correct. And you can leave the answer at this stage, or you can leave the answer at this stage if you follow this particular method, this particular approach. That's the solution for this particular question. In the fifth question, we have sine cube x into cos cube x. How do we deal with this one? So sine cube x, cos cube x can be taken care of using, there can be various approaches. One of the approaches is that I observe a sine x into cos x power 3, right? So sin x times cos x can be written as, I can write sin x times cos x as, please observe, sin 2x by 2, and there will be power 3, right? So one of the ways could be that I write sin x times cos x power 3, and this will convert to sin 2x by 2 power 3. Okay, and this is actually, okay, this is 1 by 8, okay, that's okay, sine cube 2x. Now I can integrate sine cube 2x, since I've just seen in the previous question how to integrate this kind of expression, right? So there were two approaches to follow after this, right? That is, we can use the formula for sine 3 theta and write it in terms of that, or we can directly separate sine square 2x and cos 2x, sine 2x, and we can use substitution over there. Can we use some kind of an idea, similar kind of idea, that first method which you used in the previous question, can we use a similar kind of idea over here also? Maybe. So we have sine cube x, cos x. Can I take one cos x separate? Can I take one cos x separate? Yes, maybe. I can write this as sine cube x into cos square x into cos x. Okay, so what do you want to do with this? What I see is this cos x is nothing but the derivative of this sin x, right? Okay, so I can assume, I can substitute sin x equals to t, and the derivative is present with sin dx, right? and that substitution will help me. Yes, so let sin x equals t. That tells me that cos x dx will be equal to dt. Now with the help of this substitution, I can write I equals integral of this sin cube x is actually t power 3. Cos square x is nothing but 1 minus sin square x, right? So 1 minus sin square x, which will be this, and cos x dx will be dt. This is what I get. Is that okay? Yes. This can further be simplified as t power 3 minus t power 5 times dt. Yes or no? Yes. And this integral is pretty simple now. This integral will be t power 4 upon 4 minus t power 6 upon 6 plus constant of integration. Now what is this? This t is actually sin x. So this is 1 by 4 sin power 4x, right? Minus 1 by 6. This becomes sin power 6x. Okay, plus a constant of integration. This is what I get, and that is my required answer for this question. But why only this approach? Could I have solved it in any other way? Yes. Oh, there was another way. No, I am not talking about that. That is there, yes. That is one of the approaches that we can follow. So this was first approach, this is second approach, and even here we had two further approaches, yes. And now we are looking at another approach. It's not very difficult, I suppose. You understand this one, right? Here I have taken this cos x separately, yes. I could have taken sin x also separately and used the substitution cos x equal to t, yes. The overall answer that will be obtained will be in terms of cos x there. Let me show it to you. What about this one? Will you not solve this one? No, I will not solve this one. This can be left to you, right? I have left it for you. So you can solve this if you want. You can solve it using this approach. We have already practiced quite a few questions of sin cube x for you, right? Let's deal with this one by integrating with the help of cos cube x can be left as it is. Sin cube x can be separated out as sin square into sin x dx. And I can use the substitution cos x equals t. What does that tell me? If cos x equal to t, the derivative of cos x is minus sin x dx equals dt. So sin x dx will be minus of dt. Therefore, I is equal to integral of t cube. Okay. Sin square x is 1 minus cos square x. Sin x dx is minus dt. Okay, this becomes t power 3 minus t power 5. There's a minus, so this becomes t power 5 minus t power 3 in the bracket and the integral with respect to t. The integral of t power 5 will be t power 6 upon 6. Integral of t power 3 will be t power 4 upon 4 plus a constant of integration. This is 1 by 6. T power 6 is equal to t power 6 is cos power 6x minus 1 by 4 cos power 4x plus constant, and that is the required answer for this question over here. That's what you have. So this particular answer and this particular answer should be same. Yes, they are exactly same. That's what we mean to say by this expression, right? They're exactly same, and this or this can be left as the correct answer. Both the approaches are correct. Similar approaches, right? Not very different. You can see. That's all in this particular question. The sixth question, we have sin x into sin 2x into sin 3x. Okay, and how do we handle this one? So sin x, sin 2x, sin 3x will tell me that we need to write the products of sin A into sin B as sum or difference of two cosine or sine, right? So product of trigonometric ratios into sum or difference of trigonometric ratios is the identity. That transformation is required. I have two signs, right? I have three signs actually. I'll combine any two signs with the help of this result. 2 sin A sin B is equal to cos of A minus B first minus cos of A plus B. This is the result that we have. Cos of A minus B is actually equal to cos A cos B plus sin A sin B. This is cos A cos B minus sin A sin B. Subtracting them will give me 2 sin A sin B. Right? This is what you get. That is the result that we borrowed from trigonometry, and now we'll use that result for this I equals integral of sine x, sine 3x. Let's bring them together. Sine 2x can remain outside, separate. Okay. And I'll combine these two. So what will that give me? Integral of that sine 2x will remain as it is. In the bracket, I'll have sine A, sine B. First of all, I'll have a half. Okay. This 2 will go in the denominator, half of this whole expression, which is cos of difference of these two. Now, difference of these two, yes. Why I'm saying difference of these two? Because cos A minus B, B minus A will not make a difference. Right? Similarly, A and B can be interchanged between x and 3x. So, minus x or x minus 3x will give me basically cos of 2x or cos of minus 2x. Once again, cos minus theta is equal to cos theta. So, this is what you get, right? Cos 2x minus cos sum of these two, which is 4x. This is what I have. Yes. Times dx. That seems okay. Yes. Next, this half will come outside the integral sign. And what do we have? We have sin 2x into cos 2x. Minus you have sin 2x into cos 4x. Okay. Dx. And when I observe this expression, sin A cos B, I recall another trigonometric identity, something similar to this transformation. Once I recall this is sin A cos A actually, right? So let's use those ideas. 2 sin A cos A, if these are same, then this becomes sine of 2A. Simply this, right or not? Whereas if you have 2 sin A cos B, this is equal to sine of A plus B plus sine of A minus B. So using these two identities, I'll simplify these two expressions over here, this integral over here. Half is okay. Integral of sine A cos A, that is 2 sine A cos A will be equal to sine 2A. This becomes half of sine 4x, and this can be integrated easily, right? What about this one? Sin A cos B. Sin A cos B will be again half times something. So what do we have? We have minus half times something in the bracket. And what will that bracket have? Sin of A plus B, which is sum of these two, minus, actually you have a plus sin of A minus B. Now A is the angle that is there with sine, B is the angle that is there with cosine. We cannot interchange them, mind you, right? And therefore lies the difference. So A minus B will be 2x minus 4x, that is minus 2x. And sine of minus 2x is what I'll be getting over here. Yes. Okay, this is first term minus half times the second term, and there's a curly bracket, the bracket will end over here. This is dx. That's the complete expression that we have, right? And sine of minus 2x will be equal to minus of sine 2x. That's something that we know. So I'll bring this half and this half outside. What I'll get is 1 by 4 on the outside. In the integral, within the integral, I'll get sine 4x minus sine 6x. This minus will go here and this minus will make it plus sine 2x. This is what I get. Okay. So up till now, what have you done? You have simply converted this into 1 by 4 times this expression. This is all trigonometry. Now comes the turn of integration. So integration is not difficult, right? Converting this given expression and realize into integrable form. First of all, realizing that this cannot be integrated directly with the formula that we know. And once we use trigonometric identities to convert into integrable form, after that integration is not difficult, right? So therefore, I will be equal to 1 by 4 is waiting outside. Okay, let it wait. In the integral, you have sine 4x. The integral will be equal to minus of cos 4x, and you have to divide by this 4, right? Sine 6x. So that will be minus of cos 6x. So that becomes plus cos 6x upon 6. Then you have sine 2x, which becomes minus of cos 2x upon 2 plus a constant of integration. That seems like the final answer. Yes, at max what you can do is you can multiply this 4 inside, or you can leave the answer at this stage. What you get is 1 by 24 cos 6x minus 1 by 16 cos 4x and minus 1 by 8 cos 2x plus constant. This is the form of answer, or this is another form of the answer. Leave the answer at this stage or this stage. That's all in the 6th question over here. The 7th question says we have sine 4x into sine 8x. This looks simple. Yes, sine 4x into sine 8x. We can handle this with the help of identity. 2 sine A sine B. This is cos of A minus B minus cos of A plus B, right? Since these are two sines, cos of A minus B will come ahead. And using this identity, integral I, which is sine, let's write 8x first and sine 4x later dx. This will convert to sine A sine B, which will be equal to half of, okay, let's take the half outside, cos of A minus B, cos of difference of these two, which is 4x minus cos of 12x dx. This is what you have. Half is okay. The integral of cos 4x is also very simple, that is sine 4x upon 4. Cos 12x, the integral is sine 12x upon 12 plus a constant of integration. And yes, that seems like the final answer, except for what you can do is you can simply multiply this 2 inside. 1 by 8 sine 4x minus 1 by 24 sine 12x plus a constant of integration. This tells me minus 1 by 4 sine 12x plus constant, and that is the required answer for the 7th question over here. 8th question says you have 1 minus cos x upon 1 plus cos x. Okay. How do we handle this one? Should not be difficult. If you remember something called trigonometry, some expressions of trigonometry. What is that? 1 minus cos x is actually 2 sine square x by 2, and 1 plus cos x is 2 cos square x by 2. You should remember that this overall is equal to tan square x by 2. If you remember this. If you don't remember this, I have explained that, right? Written that in front of you. Now you can integrate, right? I know the integral of tan square. Oh, do I? No, not exactly tan square, but I know how to find the integral of tan square. Yes. So I will be equal to integral of 1 minus cos x over 1 plus cos x dx, which simplifies to integral of tan square x by 2 dx. And what is the integral of tan square? How do we find that? So tan square, I don't know the integral of tan square. I know the integral of sec square, and yes, this can be converted in terms of sec square. Yes, easily. So this is equal to sec square x by 2 minus 1 dx. Okay. Sec square something that is a linear polynomial of x. Sec square integral will be equal to tan that linear polynomial, except for the fact that you need to divide by this coefficient of x, which is 1 by 2. Okay. 1 with respect to x, the integral is x plus a constant, and this converts to, this 2 goes at the top, this is 2 tan x by 2 minus x plus c, and that is the required answer for this particular 8th question, as you can see over here. Question number 9 says we have to integrate cos x upon 1 plus cos x. How do we handle this one? So in the previous question we had 1 minus cos x upon 1 plus cos x. We converted it into half angle, right? Tan square x by 2. This 1 plus cos x in the denominator is actually creating a problem, and for handling that, once again we'll have to deal with half angles. Yes. So 1 plus cos x can be simplified. We know how to simplify 1 plus cos x. 1 plus cos x is equal to 2 cos square x by 2. Okay, this looks simple, but what else? We have cos x in the numerator. What will that simplify to? So cos x, okay, that is creating a problem. It also needs to be converted into half angle, and which half angle should I convert it into? We can convert in terms of cos square x by 2, and we have 2 cos square x by 2 minus 1 actually. So I can convert it into this form. So I can use those two results, and for solving this this is cos x over 1 plus cos x dx. This will convert to, okay, integration of cos x, which is 2 cos square x by 2 minus 1 over, this is simply 2 cos square x by 2 dx. The benefit of writing it in this form is this upon this is simply 1, right? Okay, minus 1 by this whole thing, 1 by 2 is okay. In the denominator you have cos square x by 2, which can be written in terms of sec square. This becomes sec square x by 2 dx. This is what we are looking forward to. And sec square, we know how to integrate. 1 is very easy to integrate, therefore I will be equal to integral of 1 with respect to x is simply x. Minus 1 by 2 is okay, this is a constant. Integral of sec square, linear function of x, will be tan of that linear function of x divided by this coefficient of x, which is 1 by 2. Okay, this is 1 by 2, this is 1 by 2. In the denominator and the numerator will get cancelled. Okay, there is a constant of integration as well, right? Since you have integrated this complete, this tells me you have x minus tan x by 2 plus constant. That is my required answer for this question over here. That's the 9th question for us. 10th question has sine power 4x. Now how do we handle this sine power 4x? Okay. So sine power 4x, can I separate one sine x and maybe substitute something in terms of cos x? That will create a lot of complications actually if this is not a power which is odd power. Had this been an odd power, I could have written as we did sine cube x, right? We can write one sine x separate, and the remaining sine square x can be written in terms of cos square x, and I can substitute cos x equal to t. Here if I take one sine x separate, what I will be left with is sine x, sine cube x. Now sine cube x conversion in terms of cos x will be difficult, and after that substitution will make things complicated, right? So even powers of sine or cosine could be handled by using conversion to multiple angles. Simple idea of conversion to multiple angles. So what do we have? We have sine, the idea is sine square x can be written as, actually 2 sine square x, but it can be written as 1 minus cos 2x. And this is the result that we'll use. For converting that, sine power 4x. Oh, but we have written result only for sine square x. Yes, we'll apply this result maybe twice. Yes. So I is equal to sine power 4x dx, this integral. This becomes integral of actually sine square x squared. This sine square x square dx. This sine square x, I'll write it as that. So this is 1 minus cos 2x upon 2 square dx. Yes. This denominator 2 will be squared and it will become a 4, can be taken outside. Integral will have a minus b square, which is a square, minus 2 cos 2x plus cos square 2x. This is what I'll get. Observe this carefully. This is what I get, right? A square minus 2ab plus b square. That's what you have done. This denominator 2 converts to a 4 and it comes outside. This is easy to integrate, this is easy to integrate, but this still is a bit difficult. So once again, a similar result for cos also exists. That cos square x or cos square theta is 1 plus cos 2 theta by 2. And again, we can use this result over here in the last term. What do we have? This is 1 by 4 integral of 1 minus 2 cos 2x plus cos square theta is 1 plus cos 2 theta, which is 4x whole divided by 2 dx. Now each term is integrable, right? And this is the form in which we can integrate. But one more simplification can be done. Yeah. Therefore, I is equal to, I have a 1 by 2 and I have a 1. Do you observe that? Yes. So these can be added. Yes. So I have 1 by 4 on the outside. Inside the bracket, I'll have integral of 1 will not be difficult. Okay. So integral, can I add this 1 and 1 by 2 first time? Yes, I can do that. Or for the time being, let us keep them separate. Integral of 1 is simply x with respect to x. This is integral of cos 2x. Minus 2 is okay. Cos 2x, the integral will be sin 2x. And you have a 2 in the denominator because of this 2x. Right? Plus you have 1 by 2. This becomes x by 2. Plus you have a 1 by 2 already there. And you want to integrate this cos 4x. The integral of cos 4x will be sin 4x upon 4. And you have a constant of integration. So these are the terms that I'll be getting. 1 by 4 is waiting outside. Okay. X plus x by 2 is 3x by 2 minus of sin 2x. And this is plus 1 by 8 sin 4x within the bracket plus constant. And yes, that is the required integral. That's the final form in which we need the integral. At max, you can multiply this 1 by 4 inside. That is all that will do. This is the 10th question for us. In the 11th question, we have cos power 4 2x. Oh. How will we handle this? Once again, in the previous question, we saw some identities, similar identities will be useful over here. This is even power, right? So we'll have to convert into multiple angle, right? Okay, using this identity, cos square theta is 1 plus cos 2 theta by 2. Okay, this is what we have, yes. So let's use this identity. I is equal to integral of, this can be done as cos square 2x square dx. This is what I'll write it as, yes. And therefore, I can use this result and it converts to this equals to integral of cos square 2x can be done as 1 plus cos double of this angle, which is 4x by 2 and its square dx. I can write it as this. Yes. This square of 2 in the denominator will come outside. This will become 4 and you get an integral. 1 square is 1 plus 2 times cos 4x plus you have cos square 4x dx. This is what I observe. What next? So this is integrable easily, this is integrable easily, but this is not integrable easily. Once again, we can apply similar result over here to convert this into further multiple angle. This 4x will convert to 8x. Let's do that. 1 by 4 is okay. Integral is okay. 1 plus 2 cos 4x is okay. This is in the bracket. Cos square theta is 1 plus cos double of this angle 8x by 2 is what I get in the bracket dx. Is that okay? Yes. Now each and every term is integrable, therefore I is equal to 1 by 4 is waiting outside. In the bracket, what do we have? We have 1 and that 1 integrates to x with respect to x. This is 2 cos 4x, so that will be 2, okay. The cos 4x integrates to sin 4x upon 4 plus you have 1 by 2 over here. That integrates to x by 2 plus you have 1 by 2 with cos 8x as well, and the integral of cos 8x will be sin 8x upon 8 plus a constant of integration which is required. Yes. So what will this give me? This is 1 by 4 on the outside. In the bracket you have x plus x by 2, which is 3x by 2. Then you have 1 by 2 sin 4x plus you have 1 by 16 sin 8x plus a constant of integration, and that is the required answer for this question, as you can see over here. That's the 11th question for us. The 12th question says you have sine square x over 1 plus cos x. How do we handle this one? Think. This is a relatively pretty simple question. The questions that we have been seeing up till now were pretty decent, but this is pretty simple one. I is equal to integral of the sine square x. Can I write it as in terms of cos square? Oh, but what do you want? Why do you want to write it as this? Why not convert this 1 plus cos x into half angle? Don't go anywhere there. This is 1 minus cos square x, or is it actually 1 square minus cos square x, right? This is a square minus b square. Can be written as a plus b a minus b. Yes. Oh, yes. This is the important thing. This was pretty simple. Yes, this was pretty simple. 1 plus cos x, now you can see this particular term of the denominator which was creating a problem gets cancelled, and what remains is 1 minus cos x in the numerator dx. Integration of this 1 minus cos x is not difficult. Integral of 1 with respect to x is x, integral of cos x is sin x, and you have a constant. That's the required answer for this question as it is. That's the solution of this. Yes, complete solution. Don't need to do anything much. The 13th question, what do we have? Cos 2x minus cos 2 alpha upon cos x minus cos alpha. Do we need to apply cos c minus cos d? Once again, think. I is equal to this. Applying cos c minus cos d will actually not take you anywhere. Will not take you anywhere. Cos alpha is a constant. Cos x is the variable. Yes. We are integrating with respect to x. So what I can do is cos 2x. Can I write cos 2x in terms of cos x? Yes, I know. Cos 2 theta is 2 cos square theta minus 1. Try to use this one. So cos 2x is, if you are still not able to get that, please try solving this question on your own first and then see the solution. This is 2 cos square x minus 1. Okay, minus of 2 cos square alpha minus 1. Oh, why complicated this? We are not complicating this anything over here. Simply writing it as this. In the denominator you have cos x minus cos alpha, and now many of you would be able to observe that where are we heading with this? Yes. Integral 2 cos square x minus 1 minus 2 cos square alpha, and this becomes plus 1. Oh, this minus 1 and 1 gets cancelled. Yes, that's where we were heading first of all, but that's not the end. We still have one more step to take care of. What is that? This 1 gets cancelled, and if you observe, you can take out 2 common from the remaining 2 terms. In the integral you will have cos square x minus cos square alpha, and in the denominator you have cos x minus cos alpha, and now it is easily observable that you can use a plus b, a minus b in the numerator, right? You can factorize the numerator. So cos x minus cos alpha, the term will get cancelled. This will convert to 2 times integral of cos x plus cos alpha. Integral with respect to x. 2 is okay. Integral of cos x is simply sin x plus integral of cos alpha is, it's not sin alpha, right? Cos alpha is a constant. So this constant will remain as it is, and integral of 1 is x plus a constant of integration. Right? Don't make a mistake over there. This is 2 times sin x plus x cos alpha plus c, and that is my answer for this question over here. That's the final answer. Yes, this is the 13th question for us. The 14th question says integrate cos x minus sin x upon 1 plus sin 2x. How do we handle this one? Okay, there is an x, terms of x in the numerator and terms of 2x in the denominator. So these are different angles. First of all, that is an issue, right? Had there been higher powers, we would have maybe thought of converting these into 2x, right? But we don't have higher powers over there. Can we get higher powers? Maybe multiply with cos x plus sin x. That will make things complicated. Will it not? Yes. You will get a cos 2x in the numerator, but you will have cos x plus sin x in the denominator. What will you do with that? Denominator becoming more complicated is not something in which direction we want to move. So let's think of converting this 1 plus sin 2x into half angle. That is in terms of x. Add 1 plus sin 2x. We recall something related to 1 plus sin 2x. The important thing is 1 plus sin 2x can be written as this one. I'll write it as sin square x plus cos square x, and I'll write sin 2x as 2 sin x cos x. So this is actually a square 2ab plus b square, which can be written as cos x, or precisely basically this is sin x plus cos x. Let's write it as a square plus b square plus 2ab sin x plus cos x squared. Oh, why not as cos x plus sin x? Doesn't make a difference. Then why? We'll see, right? So cos x minus sin x upon this is what I have. Can I write it as this? Yes. Integral I will be equal to cos x minus sin x over cos x and its square. How will this simplify anything? Observe once again. Don't get irritated. Observe that okay, this is a complicated expression, this is a complicated expression, there is a square of this complicated expression. We should avoid squares. We should have had this been a pretty simple thing, but this is not simple. But if you observe the derivative of this expression, too complicated expression, there should be, why forget substitution? We can apply substitution still, yes. So sin x, the derivative is cos x, the derivative is minus, oh, the derivative is present with the dx, yes. So I'll use this substitution. Is equal to t, and that tells me the derivative of sin x is cos x, the derivative of cos x is minus sin x times dx, which is equal to dt. Yes, this is what you have. Okay, now I can write it easily. Yes, therefore I is equal to integral of cos x minus sin x dx, which is dt in the numerator. In the denominator you have sin x plus cos x t square. This is actually t power minus 2. The integral will be minus 1 by t, or you can solve using your steps. What is that? Therefore I will be equal to t power minus 1 upon minus 1 plus constant, which is minus 1 by t plus constant, and which tells me that I equals minus 1 upon t. T is this sin x plus cos x plus c. That is the required answer for this question, as you can see over here. Simple, yes. 15th question says you have to integrate tan cube 2x into sec 2x. How will we do that? I see some kind of a derivative here as well. Derivative of something. Do you observe sec 2x into, had there been only one tan 2x, that could have been the derivative of sec. Yes. So I'll write I as, let's keep tan square 2x together, tan 2x and sec 2x together with respect to x. Now sec theta tan theta is the derivative of sec theta. Do we have sec theta over here? Hidden actually, but we have a sec theta. This is actually sec square 2x minus 1 times sec 2x times tan 2x dx. And now comes the important step of substitution. Let sec 2x, not sec square x, sec 2x let sec 2x is equal to t. If sec 2x is equal to t, then the differentiation sec 2x times tan 2x. Derivative of 2x will be 2 times dx is equal to dt. Sec 2x tan 2x dx, sec 2x tan 2x dx, this 2 will come over here, and therefore I will be equal to integral of sec square 2x, which is t square, minus 1 times dt by 2. Is what I'll be getting, right? This 2 can come out. Integral of t square is t power 3 by 3 minus integral of 1 is t plus a constant of integration. And therefore final answer that you'll obtain 1 by 2 is okay. Let's substitute back. This t is sec 2x. So this is sec cube 2x. 1 by 3 is outside minus sec 2x plus constant, or you can write it as 1 by 6 sec cube 2x minus 1 by 2 sec 2x plus constant. That is the answer for this question over here. 15th question for us. The 16th question says that you need to integrate tan power 4x. Now how do we do that? Okay, integral of sec square x is known. Integral of tan square x can be found with the help of sec square x. Now what do we do with tan power 4x? So tan power 4x or such even powers of tan square x, or even or odd powers for that matter of tan square x, tan x, what can we do in such cases is, the first thing that we'll do is write it as tan square x times, take one tan square outside basically, and the remaining thing is basically this tan square, right? Had there been tan power 6x, so you'll take tan power 4x into tan square x, and the other tan square x will be written in terms of this sec square x minus 1 is tan square x. Now the benefit of this is, please observe, any higher power of tan square x, any higher power of tan x can be solved with the help of the sec square x, because the derivative of that is sec square x, right? Yes. So I can separate this out into two terms. This is tan square x into sec square x minus integral of, I'm writing it as a separate integral over here, tan square x dx, okay, and this is also dx, there's a minus inside. So I've written that single integral as difference of two integrals over here in terms of two integrals, two separate integrals, and observe that any higher powers of tan x will simplify in this manner only. Tan power, let us say you had maybe tan power 7x, so this will be tan square x and this will be tan power 5x. Tan power 5x over here and tan power 5x over here. So from this tan power 7x example, if you had tan power 7x, you have reduced this to a simple form and this to a lesser power form. Yes or no? Yes. And now this can be solved easily, and this can be solved again using a similar approach by converting this in terms of sec square x. Yes. So here we had tan power 4x, this is tan square x. Yes. I can use the substitution, let tan x equals t in this one. So that tells me sec square x dx is equal to dt for this one, mind you, okay, and this integral will convert into what? This is integral of t square times sec square x dx, which is dt, minus this integral. What does this integral convert into? I'm not substituting anything over here. Tan square x is actually sec square x minus 1, and this is very easy to integrate, right? This is very easy to integrate. So therefore I is equal to, the integral of t square is t power 3 by 3 minus, what about this one? The integral of sec square x is tan x. The integral of this one is x, so tan x minus x, plus a constant of integration. At the end you need to substitute this t back in terms of tan x. This is tan cube x. So this is 1 by 3 tan cube x minus tan x plus x plus c, and that is the required answer for this 16th question, as you can see over here. Is that all? Yes. The 17th question has this sine cube x plus cos cube x over sine square x cos square x. How do you handle this one? Okay, so for handling this, I recall seeing something similar in the first exercise. Where did we see that? Okay, sine cube x upon sine square x will only leave a sine x in the numerator. You have sine x in the numerator and cos square x in the denominator. Yes, that can be simplified. Yes. So I is actually equal to integral of sine x upon cos square x plus cos x upon sine square x by separating the two terms. Yes or no? Yes. And this is sine x upon cos is 1 tan x, right? And you have another cos over here. This will convert to tan x into sec x. Plus you have another term over here. Cos upon sine is cot x. And 1 upon sine which remains is cosec x. Dx. Now, this integral is very simple and this integral is very simple. These are all standard integrals. This is sec x and this here is minus of cosec x plus constant, and this is the required answer for this question over here. That's the 17th question for us. Pretty simple. The 18th question has cos 2x plus 2 sin square x upon cos square x. How do we handle this? So in the denominator you have cos square x, okay, that can go in the numerator and it will become a sec square x, easy to integrate, but you have a big complicated expression over here. Oh, there's angle 2x, there's angle x as well. So one of the approaches is we can convert this into higher angles, or we can convert this, since we have 2 sin square x, cos 2x, you remember, is 1 minus 2 sin square x. Yes. So cos 2x plus 2 sin square x. Using that, you can observe that this is 1 minus 2 sin square x plus 2 sin square x. Okay. These get cancelled. In the denominator, you have cos square x dx. This gets cancelled. This is 1 upon cos square x, which is actually sec square x dx. Integral of sec square x is simply tan x plus a constant of integration, and that is the required answer for this question. That's all. 9th question has sin x and cos cube x, but they are in the denominator. Yes. Can we make some kind of a substitution over here and simplify this? Yes, maybe. What do we have? So, in such questions, when you observe that in the denominator you have sine power nx into cos power mx in the denominator. So what do we do in such cases? If m plus n is equal to even integer, m plus n, m plus n are in the m and n are in the denominator, right? If m plus n is an even integer, somehow you have to use the substitution tan x equals t. You have to use the substitution tan x equals to t. That's something which I am telling you for now. Some integration methods and integration steps are very critical, and this is one of those steps. You don't directly get any feel from here that you have to substitute tan x equal to t. But tan x equal to t is the way in which we will be solving this. How do we handle this one? Right. So first, let's try to convert in terms of tan x somehow. What you do is I equals integral of 1 upon, I divide by cos x over here, I multiply by cos x over here, and this converts to tan x into cos power 4x dx over here. This is what I get. Okay. What else? One of the cos square x or complete cos power 4x can go in the numerator, and what you'll get is sec power 4x, which can be written as sec square x into sec square x over tan x dx. Now this is the important thing. If m plus n was even in the denominator, then you get actually sec power 4x, and from that even you can actually take out one sec square x common, is still left with a even term over here, right? So sec square x, this sec square x or any even power of sec basically any power of sec square x can be further written in terms of tan x, right? So this whole expression, in this whole expression I see a tan x. Let at this stage I can substitute tan x as t because the derivative is more present over there. And this is the step that we want to follow. The idea, I've already shared that idea with you, and this is something which we need to remember, right? We need to remember, yes. So this converts to I equals integral of sec square x is tan square x plus 1. Yeah, 1 plus tan square x. So this is 1 plus tan square x over, in the denominator you have tan x t. This is sec square x dx, which is dt. Okay. Now that reaches a form which can be integrable, which tells me I is equal to integral of, you observe this is 1 by t plus t dt, and this 1 by t can be integrated. 1 by t is equal to log mod t plus integral of t is t square by 2 plus a constant. This is what you have, and this converts to log of mod t, t is tan x, plus tan square x by 2 plus constant. That is the required answer for this question from here to here using this idea, right? That's a complete solution of this 19th question. In the 20th question, we have cos 2x and sin x plus cos x square in the denominator. Now cos 2x, if you remember, this can be written in terms of, one of the ideas is, this can be written as cos square x minus sin square x, right? We can convert this in terms of x, or in other words, we can also use another idea. What is that? This will simplify to 1 plus sin 2x, right? Ultimately, we'll have to use substitution. This denominator, one of the denominators, will convert in terms of numerator somewhere, right? So 1 plus sin 2x is easy to handle. We can deal in terms of 2x, yes. The derivative is present in the numerator. So if you want to convert this in terms of 2x, what will this be? This is cos 2x in the numerator. In the denominator, you will get 1 plus sin 2x on simplification. On expanding this, this is sin square plus cos square, which becomes 1, plus 2 sin x cos x, which it becomes sin 2x, right? And now I can take, let 1 plus sin 2x equals t, that tells me 0 plus cos 2x times 2 dx is equal to dt. Using the substitution, therefore I becomes equal to integral of cos 2x times dx is dt upon 2, okay, and 1 plus sin 2x is t in the denominator. This is 1 by 2 log of mod t. This is what I get. Obviously, there is a plus constant of integration. This converts to 1 upon 2 log of mod 1 plus sin 2x plus constant of integration. This is what you get. Okay. You could have solved using another idea, that is this. I could be written in terms of cos 2x can be expanded as cos square x minus sin square x, and this is sin x plus cos x squared. This is cos x plus sin x, cos x minus sin x. Cos x plus sin x will get cancelled. In the numerator, you get cos x minus sin x, and in the denominator, you have sin x plus cos x dx. Do you observe that the derivative of denominator is present in the numerator? If sin x plus cos x is equal to t, then cos x minus sin x times dx will be equal to dt, which is there in the numerator. So therefore I is equal to integral of dt upon t, which is log of mod t plus constant, and this is log of mod t. T is sin x plus cos x. Are this and this exactly same? Yes. You multiply with the 2 and divide by 2, take that 2 over here in the power, and you get the same form over there. This or this. Both are correct, right? That's the final answer for this solution for this particular question. Question number 21 says, if we need to integrate sine inverse of cos x. How do we handle this? Inverse functions, yes. But once again, inverse trigonometric functions we can solve with the help of properties. Now sine inverse of cos x, had this been cos sine x, sine inverse sine x is simple. Or can we convert this in terms of cos inverse? Yes, cos inverse cos x is again simple, right? And I remember that sine inverse x plus is equal to pi by 2. Okay, using this idea, can I write I equals, okay, this is sine inverse of cos x dx. This is sine inverse of something basically. I can write it as pi by 2 minus cos inverse of that cos something, right? Yes, please observe. Sine inverse x is pi by 2 minus cos inverse x, right? Simplified further, cos inverse of cos x is x. This is what you can write it as, yes. Okay, what about all the other possible results of cos inverse cos x? No, we will not be dealing with this. We will be only dealing with the standard interval over here, right? And now integration is very simple. This is pi by 2, which is a constant. Integral of 1 will be x. Integral of x will be x square by 2 plus a constant, and this is what you get. That's the final solution with the help of this result over here. This is the solution of this particular question. In the 22nd question, we have a pretty interesting expression, integration of this. Now you have cos x, but you have x minus b. Complicated, yes. These are linear expressions, right? Could be solved easily if you know certain things. What are those certain things? You need to apply a very peculiar step. Remember, in such questions, when you have cos and cos in the denominator and sine or cos in the denominator, what do you need to do? So you remember sine of A minus B is equal to sine A cos B minus cos A sine B. This is something which you are aware of, right? Okay, and if I divide this expression throughout by cos A cos B, what happens? This is sine of A minus B. In the denominator you have cos A cos B, which is equal to sin A cos B, which is tan A, minus cos A cancels, this is tan B. And. Do I know the integrals of these? Now integral of tan x, let's recall, integral of tan x dx is equal to what? Is equal to log mod sec x plus c, and this is what I'll be using. Integral of tan x is log of mod sec x plus c. This is something that we remember, and this is something that we'll be using. But first and foremost important step is what I've shown you over here. What is that? If you have these two angles of cosine in the denominator, observe that this and this, the difference of these two, x minus a minus of x minus b, the difference of these two angles is constant, yes, is a constant, yes. So I can multiply and divide by the sine of this angle. That's the important step. So I is equal to, what I do is, I multiply with sine of this difference. In the denominator you have cos of x minus a, cos of x minus b. I multiply with this difference and I divide by that difference. What is that difference? Oh, now you want to simplify this? Yes, I want to simplify this. This is actually b minus a, which is a constant, right? Integral of this whole thing with respect to x is what I am looking forward to. But this is a constant, right? It will come out of the integral. So this is 1 upon sine of b minus a. Okay, integral of this whole expression. If you observe, sine of a minus b upon cos a cos b. Sine of a minus b upon cos a cos b is actually tan a minus tan b, right? I can expand this, right, whole thing, but what I'll be getting is tan of x minus a minus tan of x minus b. At the end of the day, this is what I'll get. And integrating this with respect to x is something what I need to do next. Integral of tan x is log mod sec x. Integral of tan x is again log mod sec x. Okay. 1 upon sine b minus a will remain as it is into integral of tan x minus a will be log mod sec of x minus a. At max you need to divide by the coefficient of x, since this is a linear expression of x. Dividing by coefficient of x, which is 1, will not make any difference, right? Minus log mod sec of x minus b. This is what I get, and plus a constant of integration. Plus a constant of integration. This is the expression. Okay, and log something minus log something. Log m minus log n can be written as log of m by n, right? This is the final form, or I can write I as 1 upon sine b minus a log of mod sec x minus a upon sec x minus b modulus. This is what I get, plus constant using log x minus log y is equal to log x upon y. This or this can be the final answer. That's the form, either this form or this form. You leave the answer at any stage, and that's all. That's the final integral. That's a complete solution with the help of this important thing, right? Now there could have been another kind of question over here. You could have had sine of x minus a and cos of x minus b. If you had that kind of an expression, so you'll have to think in terms of cos a minus b, cos a cos b minus sin a sin b, and that will give you an integrable form. So in that case, you'll have to multiply and divide with cos of this minus this, and cos of b minus a will come over here, right? If these are similar functions, similar, that is, if this is cos and sin, you will have to use multiplication and division by sine, and if this is sin cos, then you'll have to use multiplication and division by cos, right? That's the important thing. With this idea, you can solve any such question coming in front of you. That's a complete solution of this 22nd question. Question number 23 says, okay, integrate this. There should be a dx over here. Yes. This is the question in front of us. Okay. So what do we have? Integral of sin square x minus cos square x upon sin square x cos square x. Is that difficult? No, that does not seem difficult. I is equal to, can I separate the two terms here? Sin square gets cancelled. This becomes 1 upon cos square x minus cos square, this becomes 1 upon sin square x dx. Separating the two terms, yes, and this is nothing but sec square x minus cosec square x. Integration is pretty simple. The integral of sec square x is tan x minus integral of cosec square x is minus cot x. This becomes plus cot x plus constant. Yes, tan x plus cot x plus c. The correct answer is this option A. Option A is the correct answer for this question over here. The 24th question says integrate e power x 1 plus x. Once again, there should be a dx over here upon cos square e power x times x. Now, this is very bad expression. E power x into x, that's pretty complicated. That's no linear expression of x, right? So we'll have to think of substituting that first of all. So let's use a substitution. Let e power x times x is equal to t. And what is the differentiation of this? E power x times derivative of x is 1 plus derivative of e power x is e power x times x. We are applying the product rule, times dx will be equal to dt. Okay, this is e power x is a constant, 1 plus x will, e power x comes out, not a constant, e power x comes out, 1 plus x dx is equal to dt. This is there in the numerator, yes, yes. Therefore, I will be equal to dt upon cos square t. Oh, this is nothing but sec square t dt, yes, and integral of sec square t is tan t plus constant. This is tan of t. T is e power x into x plus c is what I get. So tan of x e power x. The correct answer is this option B over here. The correct answer is this B. That's the correct answer for this question with the help of these steps is what you can see over here. And with this, we come to the conclusion of this 24th, this exercise number 7.3 over here. Yes, this is the 24th question, the last question of this exercise. And in the next session, we'll talk about another exercise. Till then, all the best.